Okay, so we want to see that we have this direct sum decomposition, and maybe let me recall what we have. So I mean, I have the range of pH. I have chosen orthonormal basis, which I denote by omega n, and then I'm looking on the subspace in my Hilbert space Hn, which is what I can get from the omega n by applying my Weyl operate, my wxy or st on them. So I'm taking all vectors which I get from applying wst to omega n for all possible choices of s and t. I'm taking linear combinations of those guys and I'm closing this. So then I get a sub-Hilbert space, and I'm claiming now that my representation decomposes with respect to those HNs. So more precisely, so what am I claiming? I'm saying, first of all, each of those guys is an invariant subspace for my operators, for my Weyl operators, for the W's. So each Hn is invariant if I'm acting with my operators u and v, or which is the same if I'm acting with my WSTs. So each Hn is invariant for the W, let's say x and y, for all x and y. Then, secondly, if I take two different of Hn and Hm, then they are orthogonal to each other. So B is that Hn is orthogonal to Hm if n is different from m. And then I'm also claiming that if I'm taking the direct sum of all those guys, I'm getting the whole Hilbert space. So I'm having not left out anything. So I can reconstruct the whole Hilbert space by all the vacua and acting with my W's on them. So here I'm saying that the direct sum of the Hn from 1 to capital N is the whole Hilbert space. I mean that I have a direct sum here. They are already orthogonal. So the main point here is that if I'm taking this here, this is really the whole Hilbert space, and there is not an orthogonal complement left out. Okay, and what is included here in particular is, of course, that if my representation is irreducible, then of course the capital N must be 1. And then I only have an H1. So D, because otherwise I can decompose it here. So in particular, the possible irreducible representations of the Weyl relations are given by such components here. So in particular, if the representation which I'm considering is irreducible, and I know all those things, then this means that the capital N must be equal to 1, and the whole Hilbert space is just the space which I can get from one vacuum. I mean, I only have now an omega 1 by acting with the W's on them. Good. Okay. So now let us check those. So I mean, they are more or less clear and obvious, but okay, let us still look on them. So first, so A, so those guys are invariant for this, which means if I'm acting with a W onto something in this space, I should land into this space. And this is clear because, as I already pointed out, if I'm multiplying two W's, I'm just getting another W up to some scalar factor. So this is clear, since if I'm acting with Wxy on the vector Wst omega n, which is the basic, which is the vectors which generate this here, then I know that the product of this here is some phase factor e to something, and then I'm just getting a W of x plus s and y plus t. So I'm getting just another vector which lives in this space. And of course, I mean, a general argument in this space is the limit of linear combinations of such things. But of course, this action here goes over to linear combinations, and because this here is unitary, so it also goes over to the closure. So this is not a problem. Good, so this is clear. So this means those spaces here are invariant subspaces of my representation, and the representation decomposes with respect to it. Yeah, but even more, the subspaces are also orthogonal. So why is this? So let us check this. So we should take a vector from, let's say, Hn and a vector from Hm. And again, it suffices to look on the basic vectors like this, because if they are orthogonal, it goes over to linear combinations and also to the closure. So what I should check is that if I take, let's say, a wxy omega n, so this is a vector in Hn, and I'm taking a corresponding vector in Hm, so which is ws t omega m, I should see that by some reason this is equal to 0. Yeah, okay, and so how do I see this? Yeah, for this it is good, of course, so I can only use algebraic properties. So I can bring, let's say, this to the other side. I have here omega n, and then I have here omega of, let me see, so what is the best way to do this? Okay, so it's omega, let me write it. It's omega. If I'm bringing this to the other side, it will appear as the adjoint, and the adjoint is minus x minus y, and then I have here w st acting on omega m. Okay, so this I know. This is e to some factor times w of s minus x and t minus y. Yeah, okay, but a priori it might not be clear why this should be 0, but now we recall that actually the omega m's are eigenvectors for the projection. So I mean, the omega m is the same as p omega m, and the omega n is the same as p omega n, because they are lying in the range. And so this p here, orthogonal projection, I can bring it to the other side. So I have a p star here, but this is the same as p. And now you see what I have here is now p times w times p. And for this, again, we have algebraic relations. So namely, if I'm multiplying a w from both sides with a p, then I'm just reproducing the p up to some scalar factor. So this whole thing here is purely algebraically, it gives me a multiple of p. I mean, this multiple is this guy here times the e factor which I'm getting from doing this here. But that was what I did before. I mean, I was not showing this, but I wrote down this equation that p times w times p is e to some factor times p. So p really reproduces itself. And but now you see what I have here is now, let me take out the lambda, and I have here omega n. And then I have here one p left, p of omega m. Yeah, but p omega m, of course, is omega m, because the omega m's are a basis of my range of p. So this is just omega m. And what I have here is now multiple of the inner product between omega n and omega m. But the omegas I had chosen as an orthonormal basis of the range. So which means in particular, if n is different from m, they are orthogonal to each other. So this here, this is equal to 0 if n is different from m. Yeah, and so you see, in a very nice algebraic way, we see that those spaces here are orthogonal to each other. But of course, the important point was that we have this relation PWP is a phase factor times P. which is just, coming from the Weyl relations. Of course, in the end, everything goes back to the Weyl relations, but we have to use them in a very nice way. Good. Okay, so we see that we have here a decomposition of our Hilbert space into orthogonal components. And now the question is, do we get everything by those guys here? Or could it be that we are leaving out here something? And so to see C, let us denote this direct sum here by K. And a priori, I don't know whether K is all of the Hilbert space or not. Of course, I want to show this. But let me give a name to it. So K is this direct sum of the HNs from 1 to capital N. Yeah, good. Okay, and now it could be a priori that there is an orthogonal complement. So if K is not all of H, so K is a sub-Hilbert space of H, then it would have an orthogonal complement. But then we could argue that our representation, of course, if we restrict it to this orthogonal complement, is still a representation of the Weyl relations. And we could do on this orthogonal complement what we did on the whole space before. In particular, we could see, or we could write down the projection onto the vacuum on this orthogonal complement, and algebraically it's just the same as before. So this means the projection onto the vacuum on this orthogonal complement is just the operator P, which we already have, because algebraically it would have the same form. Okay, so what I'm saying here is that if I'm taking this WST and I'm restricting them now to the orthogonal complement of K, this still is a representation of the Weyl relations, now just on a different Hilbert space, namely on this part of our whole Hilbert space. But for this representation, we could do the same as what we did for any representation. So namely, we take the projection onto the vacuum, the projection for this. Yeah, but of course, the projection onto the vacuum is given in algebraic terms, in terms of the W's, and this means this projection would be algebraically the same P as we had on the whole Hilbert space. So the projection for this would just be our P restricted to this. Yeah. Okay, and as we have seen, this projection in our representations cannot be equal to 0. That was this injectivity of this mapping from H to WH. So this means, because if we would still have here a representation, then the P restricted to this would be the projection in this representation, and we have seen this cannot be equal to 0. So this means the restriction of P to this K orthogonal complement cannot be equal to 0. So which cannot be 0. Yeah, but this means now, this means that we have a contradiction, because then there is an F. Okay, so we of course we assume that this orthogonal complement is not the 0 set. If it is 0, then of course there is no representation. The trivial representation, or the representation on the 0 vector space, that's not what we want. Okay, so then we would have a vector there which is not 0, which would not be mapped to 0. So with P of F is equal to F. So in this space, we have our operator P. P restricted to this space is not equal to 0. So there must be a vector in this space on which P of F is equal to F. Yeah, so this is not equal to 0. But of course, F is in the complement of K. But on the other side, P of F, this lies in K, because K is the yeah, k is what is generated by all the omega n, and that the omega n's were an orthonormal basis of the range of P, which means that, of course, this here must lie in K, because this is generated by the omega n's, which is a basis for the range of this. Yeah, but now you see that I have an F, which is not 0, which is in K and in the orthogonal complement, and of course this cannot be. This is a contradiction, which means this can only be the case here, that actually this orthogonal complement is 0. So there is no non-trivial rest if I'm taking this orthogonal sum. So this means the orthogonal complement of K actually just consists of 0, which means, of course, that K is the whole Hilbert space. Yeah. And again, it's very nice how we just argue algebraically. So if there would be a rest, in this rest we still would have a representation of the Weyl relations. We still would have our projection, and in particular we still would know that this projection cannot be equal to 0. Okay, and this gives us the contradiction, because this projection in the rest must just be the restriction of our projection of the whole space. So because everything is defined algebraically. Good. Okay. So this is really, I think, a very, very nice. I mean, we are working in a Hilbert space and making statements about vectors and orthogonality in the Hilbert space, but all the arguments are just algebraic. Good. Okay. So this gives us this. Orthogonal decomposition of a general representation into these parts Hn. And the Hn, of course, should be the irreducible representations. And now we still have to see that the representation restricted to each Hn must be the Weyl, must be the Schrödinger representation. So that's still what we have to see.